All right, boys and girls, we got a tough question ahead of us. It's essentially the entirety of the electrochemistry chapter boiled down into one question. And really, this is a good question because if you can do this question, then you really have mastered all the parts of electrochemistry. And so let's get down to the basic part. And I know at one point in the question it asks you to draw a diagram, but I think that's a good place for you to start. Start with this basic diagram. Now I've gone ahead and filled in zinc. Oh, here we go. Let me get this basic. There it is, basic diagram. This is the basic output. We haven't labeled anything other than the salt bridge. And so once you get to this point, just draw this picture, and then you want to ask yourself, okay, well, is the one on the left, is that the anode, or is it the one on the right, the anode? What about the cathode? Is the one on the cathode, which one is which? At the end of the day, it doesn't matter. As long as you've got the electrons flowing in the right direction, what you know is that reduction is going to happen at the cathode, oxidation is going to happen at the anode, and as long as you show everything being flowing in the right direction, then you'll have the diagram correctly. One of the biggest sort of aha moments for me when it came to electrochemistry was the realization that if you hook up the voltmeter on the wrong direction, it's not that the cell doesn't work, it's just that the voltmeter is going to read negative instead of positive. The cell still works, electrons still flow, it's just that you haven't labeled it correctly. So you got the electron flow backwards. So the big moral of the story is getting the electron flow correctly. So in the next picture, I went ahead and I kind of just arbitrarily said, okay, well, the zinc's on the left, gold's on the right. What that means is that then zinc 2 plus ion is in the solution on the left with the zinc, and the gold 3 plus ion is in the solution on the right with the gold. So that's a good place to start. Once you've decided that those are the ways to do it, then everything else sort of falls into place. So start off with this basic picture, and then go ahead and start to then put in the silver and the gold, or excuse me, or the different metals for the cathode and the anode. If your instructor says, no, I want the cathode on the right, well, okay, then you're going to have to go and do that then. But I don't think that's a fair way to do it, because at the end of the day, it doesn't matter which direction you lay the cathode and anode beakers on the table, the cell is going to work. It's all about the question of whether or not you hooked up this voltmeter correctly. So having one in one direction, one on the right and one on the left all the time, that's arbitrary, and I don't think that's fair in my opinion. So that's why I think it's okay to do it this way, because if you understand where the reduction is happening, where the oxidation is happening, then you know the direction of the electron flow. Okay, so that's kind of like the next thing we need to do. We need to get in here and start to work on the different half cell reactions. We know that it's a gold 3 plus and a zinc 2 plus half reactions. And so let's go ahead and look up those half reactions in our table of reduction potentials. Now, here's what we need to remember is that when we're looking at these, the more positive the reduction potential is, the better that substance is at being reduced. And you also have to remember, and we already talked about this, that reduction happens at the cathode and oxidation at the anode. The mnemonic is red cat, ox an. And so what that means is reduction happens at the cathode. And you have to know that reduction means gaining electrons. Oxidation means losing electrons. If you don't know the definition of reduction and oxidation, then it's going to be challenging to get this correct. So you've got to go back and you've got to have those basic definitions down. Okay, so now that we have these half reactions, we know which one is more positive, the gold, then we know that gold is better at being reduced. So then that means that the reduction is going to happen to the gold. So now we can label it, right? Red cat, reduction happens at the cathode. So boom, I label the AU as the cathode. boom, I label the zinc as the anode. Now I know the electron flow, and this is what makes the diagram correct. If the reduction is happening at the cathode and electrons and reduction is gaining electrons, then the electron flow is from anode to cathode. So you draw the electron flow in the appropriate direction to represent the correct diagram. Now, the last thing in the diagram, in order to draw the diagram correctly, is to say which directions cations and anions flow in the salt bridge. Well, it's going to have, the charge always has to be balanced, right? So you can't have a container that has negative charge just being built up into it, right? It's always got to be balanced. So if you have negative electrons flowing into the container that has the cathode, then you're going to need positive cations to balance that out. Same thing with the opposite is true. If in the anode container you have electrons flowing out of it, then you'll need negative anions flowing back into it in order to balance that out. And so that's it. Now you've drawn the diagram. So once you've drawn the diagram, then the next thing is to move on to those other questions. And it says to calculate the standard voltage of the cell, E naught cell. And so you do need to kind of bring in a formula that reminds you that E naught of cell equals the E from the standard reduction potential of the cathode minus the standard reduction potential of the anode. And so we just put those two things together. Negative times a negative is a positive. And so the actual voltage of the cell, of the entire cell reaction, is 2.2598 volts. Now, I went ahead and rewrote these two half reactions. And the reason I rewrote these two half reactions is the next thing that we want to do is figure out the standard free energy change for this particular cell. In order to do that, one of the things that we need to know is how many electrons are lost and gained. Because the number of electrons goes into the formula, and we'll see that in just a second. And take a look at the two half reactions. Gold 3+ has to gain 3 electrons in this particular reduction half reaction. Remember, half reactions are always presented to you, the reader, as a reduction, even though in the cell, reduction and oxidation is happening. So when you figure out what's being reduced and what's being oxidized, then the reduction gets written as a reduction and you flip over the other one for the oxidation. So when I'm presenting to you the reaction for zinc, I'm presenting it to you as a reduction, even though we know that we're going to flip it and zinc is actually getting oxidized. But at the end of the day, the half reaction shows zinc 2+ gaining 2 electrons to become zinc. So the number of electrons in the half reactions isn't the same. And so we need to balance those. And so what is the common multiple of 3 and 2? I just said it. It's 6. So in order to get 6 for this thing and 6 for this thing, then I need to multiply everything here by 2. I need to multiply everything here by 3. And that's why I end up with this sort of middle of the road reaction that has 3 zincs and 2 golds to balance things out. And we're going to need that later, because when we write the reaction quotient, we need to know the stoichiometric coefficients for that reaction. But the overall reaction without the electrons included, now it's 6 electrons, would be this reaction. And we'll need that later. Oops, look at that. That's 3, and it needs to be zinc. Okay. 2+. All right. Now, here's the formula for delta G of the reaction, for the standard free energy change of the reaction. The standard free energy change of the reaction equals negative the number of electrons transferred times F, a constant, times E naught of cell. All right, we've already calculated E naught of cell. we need to go ahead and get out this constant, and this is Faraday's constant. It's 96,485 coulombs per mole. And the next one is 6. That's the number of electrons that are transferred. Now, I want to point out that 1 volt, which was the E naught of cell, also equals joules per coulomb. So coulombs get canceled. Leaving me with joules per mole. And so the standard free energy change of the reaction is negative 1.308 times 10 to the 6th joules per mole. Okay, so let's move on now. So what it wants us to do is calculate the equilibrium constant of the reaction. And so the equilibrium constant has its own formula. E naught of cell equals R times T divided by NF times the natural log of the equilibrium constant. And the equilibrium constant is what we're solving for. Everything else is known. So I get 2.2598 volts equals, and then remember the gas constant in this case is joules per mole Kelvin, so it's 8.314. The standard temperature is 25 degrees, so that's 25 plus 273.15. That gets us 298.15 in Kelvin. Again, same 6 electrons and the same Faraday's constant. So recall in this next section, I went ahead and changed the volt units to joules per coulomb. Let's take a look at how things cancel. Kelvin cancels with Kelvin, mole with mole. Now, from each side of the equation, joules cancel with joules, coulombs cancel with coulombs, and I need something unitless because remember that the equilibrium constant is a unitless value. So when I do all this math, I'm going to take 2.2598 divided by 8.314, divided by 298.15, multiply it by 6, multiply it by 96,485, I get 527.7597, and that equals the natural log of K. And so remember that the natural log, so remember that the formula, the identity is E to the natural log of X equals X. So if I exponentiate in base E, then I can get rid of the natural log and isolate K. And so that's what I've done here. Now, you might need a calculator that can go this high, and not everybody has a calculator that can do it. And so you're not always going to get an equilibrium value that's this large. You can use an online solver. You can use a really nice TI-85 or TI-86 or TI-89. Should be able to get you orders of magnitude as large as this, but if you get E to the 527.7597, then you got it. That's the right answer. But in decimal notation, you get 1.6 times 10 to the 229. It's a huge number, way bigger than a mole. So it's a really big equilibrium constant. Okay, so the next thing that the problem wants you to do is use the standard cell notation to represent the cell. And just to review, standard cell notation goes like this. The first thing is the material that the anode is made out of. Then there is a phase separation line, and that single line means phase separation. Then you write down the anode solution. That is separated by a salt bridge. Then you write the cathode solution. That is also another phase separation between that and the cathode material. So what was the anode material? The anode material was zinc solid. What's the anode solution? Well, under standard conditions, it was 1 molar zinc nitrate. There's my salt bridge. What was the cathode solution? The cathode solution is 1 molar gold 3 nitrate, and the cathode material was solid gold. So there's my standard cell notation representing this particular galvanic cell. Okay, so we're almost done. I think what it wants us to do now is it wants us to determine the actual voltage of the cell under non-standard conditions. It didn't ask us to change the temperature, but it did ask us to change the concentration of the two reactants. And that's when I said way back earlier that we're going to need the stoichiometric coefficients in this reaction, because when I write down a reaction quotient, which is in this formula, I'm going to need to know what powers to raise each of those concentrations to. So the voltage of the cell under non-standard conditions is the standard voltage of the cell minus RT over NF times the natural log of Q, the reaction quotient. And the reaction quotient, remember, is the concentration of the products raised to their stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. So we don't include solids in the reaction quotient, so it really is only the concentrations of each of these solutions. So it's zinc 2 plus, there's 3 of those, that goes in the numerator, and gold, and gold 3 plus, there's 2 for the stoichiometric coefficient, that goes in the denominator. And so now what do we get? So we get the same value for RT over NF that we did over here in this calculation. So literally I'm taking all those same numbers and I'm moving them to this particular ratio. And then I'm going to go ahead, include my standard cell potential. And now I'm going to write down my natural log of the reaction quotient. And here are the 2 molarities that the problem gave you. Just remember that you have to raise them to the correct power because that's the definition of reaction quotient. Review that from your equilibrium sections. So then it's just a bunch of work in the calculator. What you get for this side, for the reaction quotient, you end up with 0.2637. For all of this mess in the middle, we can do some cancellations. We get mole cancel with mole. We get Kelvin cancels with Kelvin. And what we're left with is joules over coulombs. And that's important because a volt is a joule over coulomb. Don't forget that. So we can do the subtraction. And the value that we get there is 0.0042819 joules per coulomb. Now we have to multiply that by the natural log of 0.2637, which is negative 1.3329. So when I do that multiplication, I get 0.005707 joules per coulomb. And instead of having something that's negative, I had negative times a negative. Bam, that's now a positive. So I'm adding the value to the standard cell potential. So 2.2598 plus 0.005707, I get that the voltage of the cell under non-standard conditions specified in the problem is 2.2655 volts. Okay, I know that's a lot. It's a whole lot of work, but if you can do that, you got the electrochemistry chapter down.